Okay, so for today's morning session, Debajyoti will talk about some recent progress on excited state modular Hamiltonians.
Thanks, Nilakash, and thanks for being here, 4th week. It has been an amazing program, and thanks for giving me the opportunity to present our work here. So yeah, I will be talking about modular Hamiltonians, in particular in excited states. We have learned or listened to many talks related to modular Hamiltonians in this conference. They are very important. Gives in understanding aspects of entanglement, algebraic structure of field theories. For me, I kind of got into this, especially because I was thinking about this entanglement wedge reconstruction, extrapolate dictionary, and there has now been some recent progress on that direction in terms of this modular Hamiltonian, and we wanted to understand that more in contexts of not ground states but other states, and then we were naturally asking ourselves that whether I can write down some excited state modular Hamiltonians in maybe some perturbatively excited states, and that led to this project. We wrote a few papers on this and did some more work, and now we are, so these papers were with Dan Kabad, Gilad Lifshitz, and Phuc Yuen, and now we have some more ongoing work with Alex and Akash, who are PhD. So yeah, I mean, please feel free to stop me at any point, and if something is unclear. The talk will maybe at the end will be a bit technical, but we'll see how we do with time, and so yeah, as I said, we'll deal with aspects of density matrices and modular Hamiltonians, oftentimes maybe sub-region modular Hamiltonians, but our goal will be to understand this the extended modular Hamiltonian. So we know that if we have some factorizable Hilbert spaces like this, so suppose I have two subregions A and N complement, then and the Hilbert space is bipartition like H a tensor H a bar, then I can define for a state psi the density matrix corresponding to subregions A and A bar in this fashion. But in field theory, these are often not well defined, and what is a well defined, better defined quantity is which I will call total or extended modular Hamiltonian, which is minus logarithm of the modular operator delta. This, for example, shows up in entanglement entropy in the fashion that it becomes divergent in field theory. The UV divergences show up because QFT is essentially a continuum theory. But if it is bipartitionable, then only this minus log delta can be written as minus log of rho a tensor rho a bar inverse, and this becomes this difference between the two subregion modular. So we will compute this modular Hamiltonian and the associated total modular Hamiltonian for excited states obtained by perturbing vacuum state by a unitary operator U. So that will be our setup.
What was the point? When can we write it like
yeah, so in general, this is a better defined quantity in field theory, but if indeed this sort of factorization happens only.
And U is runs across both A and A bar.
Yeah, so I will, right here. So the state that I'll have in mind is, so let's say you have a vacuum state and you have perturbed it by some unitary operator. This operator will be for us of this form. So there is, some operator O, some Hermitian operator O, which is smeared by some suitably chosen function f, and it is smeared over, this, it's a CFTD, so some spatial or null hypersurface.
Can't you write this formally as a product of military in the two?
Yeah, we will talk about it, just, not always, but we'll see. So our framework will be this, as I said, a field theory in arbitrary dimensions D, and we'll compute the change in modular Hamiltonian to first order in perturbations, and from time to time I'll tell you when we were able to compute it to higher orders or even exactly. And for most part, the subregion will be Rindler half space. That simplifies the calculation, but once again, for some simple examples, you can do it for any finite subregion. And this non-factorizability of Hilbert space will show up in a very interesting way, and I hope you will find it interesting too.
When you say subregion, is it connected, or do you also have multi?
Yeah, so I considered like some half space from 0 to infinity as the subregion, and the rest is.
I guess I was asking generalizable multi-intervals.
Multi-intervals, I started looking at it, but I will not present that. Yeah.
If you leave aside this subtlety and do this on a lattice,
Yes.
then for this kind of unitary, the answer is clear. Right?
Yes, it is
Because
clear.
it's just a factorized
Indeed,
product and you
indeed.
So the whole issue has to do somehow with some
Yes.
UV divergences.
Yes. Yeah. I will mention about discrete system. We know everything about discrete systems.
I mean, in general, it's complicated, but for this, like for lattice,
We could do
for
it.
this case, you can do it very
Yeah,
easily.
exactly.
There's actually a previous slide. I have a small, this one.
This one. Okay.
Yeah, this one. So your A and A were, let's say, half of a system, another half you can take. Okay.
Yeah.
My confusion is this. Okay. Oh, it's just about the definition. H A and
Yeah,
H
this is
bar.
just a definition.
Okay.
Yeah.
Okay. Okay. I mean, you're not taking into account the interaction between the system and all that.
No.
Yeah, I understand.
Yeah,
okay.
yeah.
So this is arbitrarily different Hamiltonian that you're defining. This extended Hamiltonian.
Yes.
Okay.
So our perturbations will be perturbation by this, or at least towards the end of the talk, it will be by perturbations by this modular weight operator Jn, which is some local Hermitian operator. By modular weight n, I mean that if you take this operator and modular flow with respect to the vacuum modular Hamiltonian, then it picks up this factor of e to the ns. It's because for Rindler half space, this is essentially a boost. Yeah.
Local Hermitian operators.
Right.
You smear them Sarkar
Right.
unity.
Right.
Would you get such fixed modular weight operators?
So, no.
What do you want to do? Take a local?
No, just to understand what modular operators of weight n could be. Suppose in the field theory I had local operators, Hermitian. I smear them. Or even without, because he's just defining operators. If I just smear them, would I get such modular weight operators? Maybe you'll comment on this more. I just want to know.
No, I am simply saying that these Jns will flow like this, and we will see that in our prescription we only would need to use this.
No, that I understand.
Yeah.
But can you construct such operators by just taking local operators and maybe smearing them a little bit? Or do you? Maybe you'll comment on this later.
What's an example of such an operator?
Or do you have to do something?
For example, if you take T++,
okay,
that will be a modular weight 2 operator.
Okay. But it has to be.
Actually,
Can it be T plus minus in a non?
Yeah, that will be modular weight 0. So it essentially will, at least for the Rindler case, it counts like the number of plus minus the number of minuses.
For the Rindler case, it's very clear. This just the Rindler modes give you a modular weight.
Right.
For the Rindler case, I think this is just the Rindler frequency. So just this is the boost operator.
Yes.
So whatever is the Rindler modes, I think give you
Yes.
this.
Yes.
I mean, I don't know in the language of purists whether the Rindler mode can be thought of as a nice, smooth Minkowski. On this, there's no issue with divergences at the horizon and so on. I'm asking because.
I don't know, but
Okay. I mean, I would be happy with it, but there's a higher bar now.
If you're allowed to integrate with on the hyperboloid, then surely not. Then you can surely do it by integrating on a time-like hyperboloid.
Just projecting to this.
Yeah, by doing a Fourier transform on that, then you can kind of force this. But
by that criteria, wouldn't the Rindler Hamiltonian also be okay?
Yeah, I think that it's weight 0 probably. It is the modular.
But then all purists would tell me that no, it's only HA minus HA bar that is okay. You know. Sorry, not to derail your talk.
No, it's okay.
You can take a well-defined operator and do the Fourier transform, and you get a well-defined thing. Sorry, you have to do a Fourier transform, but then like you have to also figure out the modular. Yeah.
That you have to smear anyway.
Yeah,
That's like, no, but maybe this guy is a little better because the hyperboloid can be separated from the horizon. You kind of do an integral from minus, you use your just along the bootstrap.
But in the Hamiltonian,
Because maybe you have to integrate on
all along the sides.
and stop it. Yeah,
Okay.
I think it's fine. But
No, but most people would say not, right? That's the starting point here, that you do HA minus HA bar. Okay, fine, please go ahead.
Okay, yeah. All right, any other questions? Right, okay, maybe I should go on. So there have been a lot of earlier works on this, most of which are formal. So here are some references. So yeah. Sorry, any conclusion? No. What about delta H? So if you take some perturbations of this form, which factors into the subregion A and A bar, then you can see if, because G and G bar commutes, the unitary that I defined before, it factorizes into UA tensor UA bar. And then just from the definition of these density matrices and modular operators, you can show that rho A transforms this way under UA, rho A bar transforms under UA bar, and similarly delta transforms under this unitary in this fashion, where this superscript zeros essentially gives you, is the vacuum counterpart, and H transforms this way. So indeed, for a factorized perturbation, if you want to compute, for example, what is the first order change in modular Hamiltonian, it will be just simply a commutator. But this is, as I said, only true in such factorized situation. But in general, we'll see that there is this extra piece, talking only at this point at the first order in epsilon, which comes from the surface separating A and A bar, so which we'll call the endpoint contribution. Okay. And here are the, at least in some particular situations, the results. So for perturbations by Jn, you will see that if n is 2 and higher, then these endpoint contributions takes the form of light ray operators and their moments, and actually also descendants and their moments smeared over the x plus horizon. And you have a similar result for negative n minus 2 and less, which will be smeared over the x minus horizon.
Sorry, but x plus here is linear x plus or is it Minkowski?
It's t plus x. Yeah.
But which t?
Oh, the Minkowski t. And so for example, a special case is when you perturb by stress tensor. That will be kind of our go-to example always, because it's quite simple. In that case, this becomes the NA operator. Theta will be some sort of a tilt parameter, which will give you how much it deviates from the null slice. It will be some space-like tilt.
Depends on the operator.
Yeah, we'll discuss that. Yeah. Okay.
Just to go back to what we were talking, endpoint contribution in a sense comes by projecting into various Rindler modes. Because this x plus is like the I,
Right.
e to the whatever minus the Rindler modes. And then, but it's not raised.
Sorry, it's not 1, it's L.
No, I understand.
Yeah,
There's
okay.
no I there.
So I'm a little confused by what, in fact, by previous questions Sandip asked. As you said, in the case where it factorizes, there's no problem. Now, the modular operator is the one that we think is smooth, right? So, for the density matrix, if you said there was some UV subtlety, we would say fine. But the modular operator we think is the one which is smooth. So you're saying if we take a lattice regularization of the field theory, work out the modular operator there, and then take the limit, we'll miss something even in the modular operator? Like it'll somehow not work correctly. That seems strange, right? Modular operators are, yeah, we think are smooth. They
So
don't
what I
depend
can
UV divergences.
say is that this support function, if your perturbation did not have the support over the endpoint, then of course this entire thing will drop. It will vanish.
No, let it have support.
Yeah.
All I'm saying is take a lattice regularization. Then we know everything factorizes. We know the answer. Now we believe, at least the lore is, that the modular operator is smooth. You can take the continuum limit for the modular operator in a smooth way from the lattice. But you seem to be saying that if we did the lattice and then took the limit, then we would not see these endpoint contributions. That somehow we wouldn't get the right answer for the modular operator.
I mean, I would actually, maybe it's easier for me to go the other way. That I start from some, yeah, I don't know if this will help, but I would say that, my actual result is in fact this. And then when I do the lattice regularization, I miss this contribution. I mean, it just goes to 0, but does it violate some smoothness?
No, the question is that the modular, you should be able to take a limit of the lattice and get the correct modular operator, at least insofar as you're computing, like you're computing modular flow, or if you're trying to compute the relative modular operator and get relative entropy, or whatever you want to do with it, you should be able to get that by doing the lattice, I thought.
But in lattice, I would definitely, so I don't know how to frame that problem to go from lattice and take lattice regularization to 0. But yeah, I'm having hard time seeing how this will suddenly pop up. Yeah, so you need to have these F's for sure.
No, the Jn, just because you pick n, I think it's not well defined. We smear n, right? That's the usual story. Could it be that this contribution is not is very sensitive to smearing in n?
This I'm not so sure. Maybe we can, because I'm actually not familiar with this. Yeah. So this delta H commutator is essentially this. So H's are always HA minus HA bar if the system were bipartitioned. But let's say you have H0 in a field theory from modular operator, then this delta H is the commutator.
So it's basically the time development infinitesimally due to the perturbation you turn on of H, right? That commutator. Is that correct?
That's the standard lattice one.
Yeah.
The you get from the lattice.
Yeah.
No, I'm just trying to understand. And then you get an H2 and
Yeah. Actually, maybe I should go on because we will see that come out really clearly for stress tensor perturbations.
It's a modular Hamiltonian. Yeah, so you would see that in the lattice, right? Because you'd see a difference.
I think, yeah. No, please go ahead.
You're saying that because the unitary.
So I think you are absolutely right. I think this is one other way of understanding. So here when I discussed this G equals to GA plus GA bar, but in general, suppose you have a perturbation which looks like GA tensor GA bar, then the unitary does not factorize this way.
I think the contribution Ashok is saying would go away. In the lattice, I think, the other experts can correct me, I think delta is really rho left times rho right inverse. Because you can define a density matrix for left and for the right. And it is really rho left times rho right inverse. And that both rho left and rho right change in this way according to the unitary. So I think in the lattice,
it changes only when the unitary is factorized this way.
But the unitary does factorize on the lattice.
Yeah, on the lattice, yes.
So on the lattice, I think the answer can only be this.
Only commutator, I agree.
But his unitary doesn't. His unitary is sum of Fi OXI. If you see his specific unitary. those you should be able to integrate by parts, no? F of x del mu x, if it's really a total. You're saying maybe it could be f phi del mu phi, like something like the stress tensor. I see. Okay, that's a possibility. Is that I see. So there are some. So maybe the O itself doesn't factorize. Like that's somehow the point. You can't write O as sum of one.
As a result, G, yeah.
I see. Okay.
For the stress tensor.
Yeah.
In general.
Yeah.
Thanks, Ashok. Yeah.
Yeah, so we will have, of course, I mean, later the analysis will, I will mention some formulas involving GA tensor, GA bar, and we'll see that it's extremely clear that it does not factorize. Okay.
Why are you able to factorize? And for example, in theory, you have this. It's always basically that.
Yeah, all I'm saying here is that if you could have, then you would have gotten this. But indeed, that will in general not happen. So for example, I'll mention this at the end, but if you have a perturbation where the function has support on the future wedge, then you naturally do not have a factorization like GA plus GA bar.
You can somehow see that it only appears for these operators of this kind, right?
Operators of which kind?
It can't be written somehow as factorized.
Yes, yes, of course. Yeah.
Right, that might be, yes. Most operators, the lattice limit is not defined.
Okay. All right, so even before doing anything, let's just discuss that if such an endpoint term exists, what will be their properties? And so, from the property that the modular Hamiltonian annihilates the state, you can figure out that at order epsilon, the endpoint terms that must annihilate the state as well. This you can obtain by solving this equation and by using the fact that H0 annihilates vacuum. And this is indeed how these endpoint light ray operators that we have found out, or their moments, they behave. Okay. So yeah, you can show it by extending the calculations of these authors. So this is the outline of the talk. We'll first discuss the simplest kind of way of seeing that these endpoint contributions, how they can arise. By having some stress tensor perturbation, we'll deal with them in terms of conformal transformations. Because we know the modular Hamiltonian for the vacuum state, and then we can use conformal transformation. But there are other ways also of deriving the same result, but I will not discuss all of them for time constraints. And these methods can be generalized to obtain higher order contributions as well, but today I will only focus on the first order. And then at the end I will discuss these higher modular weight operators. I mean, not just T++, but higher modular weight operators. And one way of how the results that I have shown can be. So any other questions? I hope not. Which one? Jn, yeah, no, this is just some local operator Jn, some given point, yeah, and then you smear over with some function. So if it is supported on both sides, then interesting things will happen. Yeah. So I am saying Jn is, where is it? Yeah, so I am saying it's, this is a perturbation, Jn of x. N is just an index of the, so it's like if, yeah, for T++, it will be n equal to 2. This is the equation.
Right. I understand. Sorry to be so slow, but if you had a local operator, at least in the continuum,
Yeah.
What would you do to get something that transforms like this?
For Rindler, sorry, somebody
integrate, no? On the hyperbola, do Fourier transform. Are you worried about the I?
No, I'm just wondering if you integrate against the hyperboloid, you choose the hyperboloid on the left or right. Right? So then, in a sense, isn't this operator defined vis-a-vis the left or right space? But then it's still valued in the full Hilbert space across both things. I see.
It can be a right or a left operator, but is there a problem?
No, the claim was that it is valued in the full Hilbert space of H left to the extent you can do tensor product H right. And I'm just trying to understand your operator. So you take some operator which has support all over, say the Minkowski real line at time equals 0, then you smear it against a hyperbole on the hyperbole to get something.
So, for example, if you Jns are local operator. It's smeared by fx to give you.
Then
Yeah.
it will really help me at least if you could tell me from T++ how you get the nth move.
T plus n equal to 2 is T plus plus. Yeah. Yeah. So some conserved current with, let's say, m number of plus indices and n numbers of points. Yeah. Okay. So yeah, I mean, well, I think maybe this will clarify. So T plus plus is okay. So this is the modular Hamiltonian for some, let's say, finite subregion. We'll go to Rindler in a bit. This is the vacuum one, and under the action of a conformal transformation, this conformal transformation we can think of as, some linearized perturbation that we discussed before with the Hermitian operator G of the following form. Okay? Because you can, for this conformal transformation, you calculate the conformal charge and then e to the q times the state. So this will be the resulting modular Hamiltonian if you would have perturbed by a stress tensor of n equals to 2, perturbed by some support function f of z. Okay? So z's are the light cone coordinates. So then if you follow what we did before, suppose I am interested in just extracting out the order epsilon term, then I would just expand this g of z by expanding it like z plus epsilon f of z, and then I would just read off the order epsilon piece. And if you do that, you get this. Okay, simple exercise. And the first line you can check is the commutator contribution. So for g being some t plus plus and h0 has another t plus plus, you can use tt commutator to find that this result actually gives this first line. But the second line is actually there. And these are what we saw before as endpoint contribution. It vanishes if the support functions goes away from the endpoint. Endpoints are not moving. Yeah.
So this is coming because you're changing the region?
No, it's just that, so I had this non-local smearing, and the smearing was also over the endpoints. It was straddling the endpoints.
Yeah. So this is exactly the condition of this is actually you're moving the region. This is confirmed.
Yeah, so you can have part of it being translation. So if you, for example, take this g of z from the global part, then it will again vanish. Yeah.
That's what I'm saying. This is literally the condition that under the conformal transformation, the endpoint.
The reason I did not say yes immediately to you is because if you take this to be some from SL to R, let's say, then actually one can show that there is a cancellation between these two terms.
That's fine.
and it becomes.
So that's the case. There's two cases. One is when the endpoints don't move, so region doesn't change. And the second is when you're actually when they move, but in the symmetry of the document.
Yeah.
He's always looking at the half line, right? If I understand.
In this case, from U to V, we can still do U to V from some finite subregion. I can put U0 and V infinity.
Okay, so the UV which came in H0 is the interval of it.
Yes, yes. Yeah, but I will do half space in a bit.
Okay, yeah. But then.
Sorry, you already answered many times. What is UV here as well?
It's some locations, along X plus. So some U and V. So if
you just draw a figure actually.
yeah. So I mean, for 2 dimension, I mean, it's just could be some U and V. But I can take U equal to 0, V going to infinity. And I will do that in a bit, and then that will be in there. No, U, V are the coordinates of, let's say, along the t equal to 0 line. X equal to U and X equal to V.
Show the previous line, just because your H0 is defined also with respect to U and V.
Yeah, I mean, this is a very standard expression.
And this is the physical Hamiltonian.
This is the,
All that region, what exactly is this?
It's a Rinder Hamiltonian.
For this region, conformally transformed.
This is the bilocal operator. Yeah, the bilocal operator. Yeah.
Cares about the two endpoints.
it's not
It's
bilocal.
local, but the smearing function cares about the two endpoints.
Yeah. So for example, if you put equal to 0 and V equal to infinity, you will get, something like ZT plus plus, which will be
Oh, U and V is just the endpoints of the
just endpoints of the regions. Yes.
Oh, okay, that's what you mean.
Yeah, sorry about that. Yeah, these are just endpoints of the regions. And
So is it something like this is the evolution in the causal diamond formed by you and physically? Is that what it is?
yes, indeed. So this is like the killing vector times the stress tensor. Okay.
This is just some integral you do once and for all. This endpoint contribution. It doesn't depend on. It depends on only the value of the smearing function.
These ones, yeah. So I mean, we can zoom into the endpoints by taking, let's say, some support function of this kind, and if you can also take the Rindler limit, and then if you take, for example, this A and B to 0, then it picks out the NX operator contribution that we talked about, or from the last 2 terms.
So here, your G is this thing, which is given by some conformal transformation.
This is the G. I mean, eventually this capital G is, I mean, if you compare this with our previous way of writing the.
So this generates some conformal transformation.
Yes.
And this del H, this H is also in the conformal algebra for Rindler, right?
Yeah, so you just start with the vacuum modular Hamiltonian, you do some conformal transformation, and you get an exact modular Hamiltonian actually for the.
Del H should also be a part of, because it's a commutator of H. It should also belong to the, there should be some conformal transformation. The del H, which is a commutator of G, which belongs to, which is a conformal transformation, and H, which is also.
Yeah, there is some algebra between them, indeed. So I think I exactly forgot how it goes, but H0 comma delta H, I think it's like del U H0 or something like that. So this is one simple example where you see that quite explicitly that these sort of contributions are there. I mean, of course, I mean, if you would have naively taken A and B to 0 to begin with, then you would be missing such contributions.
flow after the perturbation in the causal diamond. Correct? Is that correct? So given U and V, I can construct a causal diamond.
Right.
The natural object would be, the evolution of theta.
Yeah, so this H0, so if you draw a causal diamond out of this U and V, this H0 flows the operator along the Rindler time
Within the causal.
within the causal diamond. Yeah, but it keeps the endpoints invariant.
Basically, that's what it is.
Yeah.
And then you have a perturbation, and this computes how the perturbation changes.
Right.
Under that.
Right.
And is there a physical interpretation of the endpoint contribution as in some flux leaving the causal diamond or something? Is there, I'm just
I
asking.
think flux.
Endpoint contribution vanishes if your endpoints are fixed.
Right.
So like it's literally coming from the fact that the endpoints are moving.
All right. Yeah. I think I know what you mean, and I think I agree with this. Yeah, yeah.
Endpoints are not moving.
So we'll make some comments about that at the end. So, yeah. Okay. Yeah. In view of time, actually, let me skip some of the next two slides. Actually, we also computed. I mean, at least for stress tensor perturbation, you can do it very easily at any orders, and it has a nice structure. So let me skip that. So let me start from here. Delta HA for a more general perturbation. So far we only talked about G being GA plus GA bar. But what if G has a more tensorial structure like GA tensor GA? So you can start with some vacuum state in Schmidt decomposed form, calculate rho A and rho A bar 0, and then you can apply a perturbation of this kind, G equals to GA tensor GA bar, and expand rho A to first order in epsilon, and the results you get are these. So GA and GA bar enters in the following way. And of course, at least to first order in perturbation, it is readily generalizable to a sum over GA tensor GA bar. So for example, GA plus GA bar is a particular example of this, where you have two terms and one's GA bar is identity and the other time GA is identity. These expressions simplify a bit if you define these modular conjugated operators by, well, for Rindler it's essentially CPT, these J operators, and the J GA bar J we call GA bar tilde. It's an operator in the A subregion, and they are related. The GA bar and GA bar tilde are related in this fashion. So if you use that, then this expression of delta rho A simplifies, and it becomes this. And as you can see already from here, that if, for example, GA bar tilde were not there or GA bar were not there, this would be a commutator. Delta rho A would be commutator between GA and rho A 0. And in fact, you can also generalize it to any higher orders, and this is the form. So by delta n rho A, I mean at nth order, what is the change of the density matrix? And once again, you see that if this term was absent, it would have been this nested commutator, as you would expect. So now there is a very nice formula that exists between delta rho A. I mean, it's essentially an expansion of the log, which relates delta rho A with delta HA. So you can plug in, and this is that formula. So what we can do is we plug in for this delta rho A, we plug in this expression, and that will be our resulting expression for perturbations of the form GA tensor GA bar. So this formula was given by in this paper. There was also another paper by Lashkari and Rajagopal and Liu, who expanded not in the subregion forms but delta in itself, and you can also use that formula, but we have used this formula. So if you do that, then I have just plugged in that expression of delta rho I showed you in the previous slide. And in terms of the modular flowed operators, where the modular flow is defined like this, if delta is only from A, only then this equation will be that equation. Anyway, so in terms of this modular flowed operator, this expression can be simplified to give this equation. So you see, this is some modular flow from some late to final modular time minus infinity to infinity. You have GA and you have GA bar tilde. You also have, as you can see, some complex modular flows, S minus I pi and S plus I pi, and we have to be careful about those if we want to extract out these contributions that I talked about.
You might have naively thought that the unitary is a factorized one, but it's not because of the endpoint contribution. And because of that, if you time evolve by amount epsilon, now the density matrix is not of a tensor product form.
Indeed.
And this is the change you're
Right. Indeed. So this change will be reflected into the modular.
I thought in this case, because it's GA tensor GA bar, it is not naively factorized.
Yeah. I think that's what you meant, right?
Okay, no, I was still, sorry, no.
So if GA is GA tensor GA bar, then U is not UA tensor UA bar.
Okay, sorry, so you're doing this case now?
Yeah, I'm doing this case now.
Okay, and then your epsilon was the amount of time evolution?
Yeah, it's like some small parameter which comes in the modular time evolution.
Then just for simplicity, of course, nothing so much to do with endpoint contribution, right? You just don't have a factorized unitary.
Exactly. I mean, the point is that this structure, that delta H is some commutator plus endpoint, it comes whenever it is not factorized, like UA tensor UA bar. Other questions? Yeah, I don't know.
Give him a little more time. So
Yeah.
it's not fair.
We'll see. Let me just go ahead and maybe I'll skip over some details of the calculations. Quite boring. But, so there are two special cases, of course. So suppose GA is identity. So the entire perturbation lies in the A bar region. Okay. So let's take G is GA tensor GA bar, but in GA bar is only what is non-trivial. Then from this equation, you immediately see that delta H is 0, which you would expect because you are not perturbing on the A region. On the other hand, if GA bar is identity, so the entire perturbation is in the GA region. Let's say the perturbation runs from some positive A to infinity, not from 0 to infinity. Then you can write down this equation in this form for some modular weight n perturbation. You can use this formula, and what it will do is it will pick up the pole at s equal to I pi, which will essentially give you this derivative term from this closed loop integral, and that if you evaluate this, if you take derivatives and so on, you will get the commutator contribution, which is once again what you expect, because if the entire perturbation is on the GA, then that means the GA, it's not of the form GA tensor GA bar in general, and you get the commutator contribution. Yeah.
Are you talking about the case where the full perturbation now is of the form?
Yeah, so I.
Tensor product GA bar.
Yes. So my.
And if GA bar is identity, then it's a perturbation which only acts on A.
That's why it's a commutator.
No, but then why is H of A is your what? Modular what is H of A?
Delta HA is the change in modular Hamiltonian at order epsilon.
At order epsilon.
Yeah.
And I thought,
so
because the density matrix for A evolves unitarily, this is the change.
Yeah. So if GA bar is identity, let's say, then it is G is just GA, right? And then it is like UA tensor UA bar where UA bar is trivial.
So this is just
Then it's just that. Okay. So, well, so then you can also consider the case where it's actually really of this form on the board, but yeah, we'll actually not do that because that's a bit more tricky. But what we will do is we will come back to, and I hope this is not confusing, so we'll come back to a form like this, GA plus GA bar. Although you can also work with this, and we have done that in the paper, and you can find endpoint contribution, but actually what turns out that even if you start with a form like this, but then still if you are very careful about what's going on near the endpoint, you can extract out endpoint contribution. So yeah, so let's say my GA and GA bar, so therefore is of this form given the G that I showed before. And here I have introduced this theta parameter, this tilt parameter. Theta being 0 is essentially the null support. Theta being 1 is essentially the t equal to 0 support. And then if you write down this previous formula that I showed, then it takes this form, of course. Any questions here? Okay, you get this equation from this equation for G equal to this. Okay. Here the unitary factorizes indeed, but I am saying that, so this is the thing. So yeah, here the unitary factorizes, but we will see that we will still, if we are careful about near the endpoint, maybe it's better if we see how the calculation goes. It's still possible to actually extract this endpoint contribution. But yeah, but there is also a derivation where I can just start from here.
I thought Ashok's point earlier was that these GAs might have derivatives.
Yeah, so essentially those types of terms will be important. But you know, if you just someone, if they have just given you this G, you would have said what Ashok just said. Yeah, so essentially I think these GAs will just move these degrees of freedom around, as you said, and that gives rise to this. Mm-hmm. Mm-hmm. Yeah, I think so, yeah. Actually, that's why this is something I forgot to mention before, that we did some intuitive, like some hand waving calculation in some sense, that to show why 0, -1 and 1, these three modular weights do not contribute. And I think the point is that there, if you calculate some equal time commutator, this sort of derivative terms do not appear. So yeah. Maybe I should just go on, I have only a few minutes left. I just want to show you like what sort of calculational techniques to use, and then we can discuss again. So there are, you know, various issues here. So first of all, there are these terms for this perturbation which apparently cancels out. And then there are these terms where you have this I pi complex modular flow. And you know, you have to be a bit careful dealing with these equations. And in fact, because this is in the operator form, dealing with, I mean, evaluating delta HA is very difficult. So what we have done is we have taken this delta HA inside a correlation function with some probe operator Jn at y, and we have chosen this y to stay somewhere on the left Rindler wedge. Okay, so y plus negative, y minus positive. So that initially, before you start doing these modular flows, there are no singularity in these correlators. But then and then we have regulated the complex modular flow. So R goes from 0 to pi, and this will give rise to various divergences when it hits, when JNY hits the light cone of this interval. And so that you have to do, you will find various divergences, but those divergences will cancel out if you keep these terms, even though it seems to be there cancelling out between each other, okay? And at R equal to pi, these correlators for both, so we have defined a new parameter w e to the minus s. So s minus infinity to infinity becomes 0 to infinity. So for both w equals to infinity and w equals to 0, they are well behaved.
Singularities, Johanna is just now in my mind some moment of 2 plus plus.
Yeah, so if you, so
And what is W here?
W is the, so I am now looking at in the modular flow. So for large early, late modular time and early modular times, there might be some, we'll discuss that. There will be some branch cuts in general, and coming essentially from these correlators, which will go away eventually when taken in this. Yeah. That case, the interval here is again half line. We could only do UV for stress tensor perturbation. Yeah. Okay. So if you compute these quantities, the correlators, basically you have to compute correlators like this for both these terms that appear here. Okay. And they give rise to these various branch cuts. And it's a bit difficult to see, but as r goes from 0 to pi, let's say I'm only talking about the upper limit a. So there will be a branch cut, a theta dependent branch cut, which will rotate and hit this integration contour from in a clockwise direction from above. There will be another branch cut from here to here, again theta dependent, but here I have only drawn for r equal to pi, which will rotate counterclockwise and hit the integration contour from 0 to infinity from below. So you have to deform the contour in an appropriate way, and the eventual contour will look like the following.
Sorry. The first two equations is a W on the right hand side. What is W vis-a-vis the left hand side?
Yeah, so yeah, these will be like these S's are related to W's. E to the minus. Yeah. So there is an integral over W, right? Here. To obtain the final delta H. Yeah. So I mean, it's not very easy to see why this will look like this, but the event when some branch cut hits the contour from top, you have to deform the contour a bit below, and then this one also a bit below from above, and then that will give you one side contour for one of these parenthesis term, and then you have to subtract from another two terms, and then you will eventually end up with a contour like this. Okay, so please trust me on this. So the eventual delta H J and Y, this integral will look like this with these various branch cuts, and from B there will be also branch cuts here, and then there is a pole at -1 coming from this cos hyperbolic factor W plus 1.
So I was thinking that the following will happen. Because you get an endpoint contribution, say for the half line, then the naive tensor factorization of time evolution would be spoiled maybe by some kind of shock wave going along the null axis, which is the causal development endpoint. And is it like that, or what is the physical meaning of this kind of result? Okay, you come to it in the end, but
yeah,
you're not fully getting a picture. Okay, please go on.
If I'm not sure if I have a very clear physical picture of this. I mean, like a shock wave, but I will mention a few things at the end. Okay. I mean, okay, let me wait till that. So once again, let's take these two special cases into account, the simplest ones. And okay, so let's say the perturbation is on A alone. So then the perturbation was from -B to A. So that means I'm looking at the case where A and minus B both are positive. And then the branch cuts will look like this. And what you can do with an extra minus sign, you can reorient your contour so that it just encircles this pole at -1, and that will essentially give rise to this commutator contribution. But but on the other hand, if the perturbation is acting on A bar alone, so minus B and A are both negative, then all the branch cuts are here. And you see, you can also close these contours here and here, because we discussed before that at late and early modular times, they actually are well behaved. Okay? So there is no problem closing the contours at w equal to 0 and w equal to infinity, and then delta H is 0. And to consider the case when it straddles the endpoint, it's even more complicated. I don't know if it makes sense to go through the entire technicalities here, but one can show that with some numerical plots that the behavior of this correlator has a bunch of delta functions like this. And to evaluate the coefficient of the delta function, you can evaluate a quantity like x plus to the k I times j. And once again, you can do similar branch cut gymnastics to eventually end up with a formula that we have shown before. Should I go through all these calculations, or should I skip? Is that okay if I skip? So it's essentially, you have to again integrate from some small region along this endpoint from minus beta to alpha. And the problems will be that in these sort of correlators, when x plus is 0, then for large W there is no problem. The correlators will be well behaved, but for x plus equal to 0 and when W equal to 0, then there will be divergences of this type. So these divergences will be of this type, that these will be bunch of derivatives of the delta function. And its coefficient can be calculated by evaluating integrals like this. And then what you do essentially is you expand this quantity in some small w, small x plus, because that's the point of interest, that's where the divergences are. And for x plus equal to 0, this second contour will also recede to infinity, and you will also only have to deal with this contour. And you will, yeah.
X plus equal to 0 is like the future in the horizon.
Yeah, so this is the x plus axis. Yes, yes, yes.
It seems like you're giving something only along that horizon.
Right. For positive modular weight. For negative modular weight, you can do a parity argument and show that you will have a delta HA along x minus.
Do the same integrals for like, you can write the modular operator as an integral like this or an integral like this also.
You mean
Maybe if I
He's computing HA.
delta HA, yeah.
So it's the right.
Yeah, so, yeah.
Hamiltonian.
Yeah,
Right.
yeah,
Is that right?
exactly.
And he's getting extra contribution localized on the horizon, right? If I understand. Localized on X plus.
Localized on x plus. Yeah. So for positive n, delta HA will be from something like 0 to infinity along dx plus. And then you can also compute delta HA bar. So these are like half light ray operators. And then when you calculate delta HA bar, you will get the other half. And ultimately, when you do delta HA minus delta HA bar, you get, so to go from delta HA to delta HA bar, you can use some CPT argument to get delta HA bar from our result. And this delta H will give you this full Leiter operators, minus infinity, infinity, but dx plus. But then when you do n less than equal to minus 2, then you use some parity argument to show you get for delta h, you will get from dx minus. Yeah. So yeah, so there is, okay, but you will get some, with some expansions and so on, you can calculate the coefficients of these delta functions, and eventually the result, let me just give you the final answer, the takeaways. This is my penultimate slide. So for this G, I should also say that when the calculation I showed you was for when the perturbation was on this effectively on this x plus x minus plane. I did not take into account the other d minus 2 directions. Okay. So, but this result is for actually for all, taking into account also the other directions. And so eventually what I'm trying to say is that for positive n greater than or equal to 2, it's an extension of the result I showed you at the very beginning, you get these Leiter operators and their moments, and for n less than or equal to minus 2, you get the same thing. So let me make some final comments. So we did discrete systems. It's in this case at least quite easy to understand. KMS conditions, we have also seen that they are verified for delta H. And we have also checked that it generates the correct modular flow. So it keeps the modular automorphism intact. So that means that we have correct modular Hamiltonians, because these two facts together should give us the unique modular Hamiltonian. We have some computations where the perturbations is, maybe with some support over here. That turns out to be quite complicated for some reasons we don't fully understand. But I can discuss it later on. I can, but it's better to discuss later, because there will be, even though it's of the form Ga tensor Ga bar, when you actually compute it, there will be, we are finding at least, hopefully we'll resolve it soon. I think we understand why we have some problems with the modular flow, but for now we are finding some subtle problems. Kind of these things are, so these two have all done, and this thing we are almost done with it. You can ask, what about similar contributions in related quantities like relative modular operator and so on. So we made some progress in that as well. Well, one can ask whether there is some algebraic derivation of these things. I don't know what I mean by this, but I wrote it anyway. And I said at the beginning that my interest was from holography. So you can also ask that if the CFT has a holographic dual, then what are the corresponding contributions in maybe bulk side? So I'm very interested in that as well. And there are also many more other questions which I can tell you about, or maybe you will ask. So yeah, that's about it. Thank you.
Question. So H endpoint was also an integral along the horizons, is it?
So say that again.
Was H endpoint also an integral on the horizons, or was it something local? Or
No, it was an integral over the horizon. So it was an integral over dx plus.
okay. So like, I understand it's just field theory, but if you also have gravity or something, you don't expect H endpoint to be something geometric from the bifurcation point or something.
In the holographic context.
I mean, if you also had gravity in wherever you're doing this calculation, not holographically, but.
I don't want to make a comment on this. I'm not sure, but maybe, yeah.
But it's a full integral, you're saying.
Yeah.
Okay.
It sum over? Yeah, so this is this n minus 2 minus k by 2. Yeah. Actually, I mean, for these modes, it annihilates the vacuum as it should. Because, you know, if you look at these papers by Kravchuk and these papers, Simon Staffin, I mean, at some point they will divert. So what they essentially do is, there is a limit like this, bound, for which you can, I mean, close the contour on either the upper half plane or lower half plane for the correlators. By putting operators like, you know, light ray operators like this, with extreme left or extreme right with a bunch of other insertions, and you can show that, you know, those correlators can be put to 0, yeah, when acting on the vacuum. Yeah.
And I'm one of these Rindler observers going along.
Okay.
On a hyperboloid. But I'm not at the horizon.
Okay.
So before any perturbations were turned on, suppose I had a free field theory to begin with, and all, I would see Rindler temperature, which would be finite, and so on. Now let's say we turn on one of your perturbations, which were of the type we were considering here, something tensor product identity plus identity plus. Then there would be, of course, some impact because the Hamiltonian has changed, etc. But there'd be nothing singular, right? The entire delta function would be localized at the horizon, safely far away from any such stuff. Right?
I think so. Yeah.
Any other questions? Okay, then let's thank Debajyoti again.